Hi, welcome back. So we're going to be working with special right triangles today. This is section 8.3, and we'll be calculating measures of special right triangles by recognizing and applying the properties of the two kinds of special right triangles. So we're looking at right triangles that have angle measures of 45, 45, and 90, and then right triangles that have angle measure of 30, 60, 90. The reason why these are special and the reason why we want to study them is because it's a shortcut to Pythagorean theorem. The only thing hard about this is that square roots get involved. All right, let's jump right on in. We're going to start with the 45, 45, 90. If I look at a square, the diagonals are going to form two congruent isosceles right triangles. Since those base angles of the isosceles triangles are congruent, the measure of each of those acute angles is going to be 45 degrees or 90 cut in half. This triangle is the one that we call the 45, 45, 90. Now we can use the Pythagorean theorem to find the relationship between the lengths of the sides, as shown right here, where we're taking the length of one leg, which we've called cursive L, squared plus the other leg length L squared equals h the hypotenuse squared. If we simplify this down, we notice that the hypotenuse is equal to the measure of the leg times the square root of 2. This is our shortcut. I'm going to put our shortcut in some colors to make it a little easier for us to see and use in the upcoming examples. So I'm going to color my hypotenuse here in red. And so the hypotenuse is going to be equal to the measure of one of the legs, which I'm going to color in blue for you. And that leg measurement times the square root of 2 will be the measure of my hypotenuse. All right, let's put this into action with example A. I'm going to zoom in real tight here on example A. Here we go. First off, I'm going to try to identify the kind of triangle that I have. I see that I have a right angle, so this is a right triangle. I also see that one of my acute angles is 45 degrees. That means that the other angle over here is also 45 degrees, and this is a 45, 45, 90 right triangle. That means I can use my little special formula that I developed up at the beginning that says that my hypotenuse, which I'm going to color in red, the hypotenuse is equal to whatever the measure of the leg is, just one of the legs, times the square root of 2. Using my color coding, I find that the hypotenuse was given to us as a variable x, and the leg measurement was given to me to be the number 6. I need to find the value of x. It's already done, and I didn't have to use the Pythagorean theorem, though you're welcome to use that as a review from the previous section to 8.2 when we looked at Pythagorean theorem to confirm that this is indeed the response. Let's look at example B because it's slightly different. Once again, I'm going to identify the kind of triangle that I have. I see that it's a right triangle because I have a right angle sitting here, which means this is my hypotenuse. And then if I look at the angles, I notice that I don't know anything about the angle measurements. They didn't tell me, but they told me the measure of the legs. And if I look at the measure of the legs, they're the same value. Sure, I don't really know, like if I took a ruler, how long I would need to measure to get 9 square roots of 2, I don't know, inches. I don't know physically how long this is, but I do know that the square root of 2 is a constant value. It doesn't change. And so if I multiply 9 times that value, whatever it is, it's not going to change. So these two legs are the same. 45, 45, 90 triangles are isosceles right triangles. And so these are the leg lengths. And so I can use my handy dandy little theorem from above that said that my hypotenuse is equal to one of the leg measurements, it doesn't matter which one, times the square root of 2. Just like in the previous example, I'm going to substitute in using my color coding. My hypotenuse was red, that's X. And then one of the leg measures, it doesn't matter which one, 9 square roots of 2. And now I have this thing which looks, oh my God, it looks bizarre. It says 9 times the square root of 2 times the square root of 2. Let me write that a little neater just because I've got this kind of looking a little messy right now. So that's 9 times the square root of 2 times the square root of 2. Okay, I need to remember how we multiply radicals together, things with square roots. I can multiply them together as long as the little index, and let me grab a different color here. The index is indicated by a little number or a letter that you'll see floating right here. As long as those are the same, I can multiply them. I know these square roots don't have an index. That's why I'm calling them square roots instead of literally anything else, because I don't see an index. It's assumed to be a 2. So this is a square root. All right, so they have the same index. They don't have an index, so they're the same, which means I can multiply them together. So I'm going to go ahead and multiply them. The way you multiply square roots is to write it as a single square root. And then inside the square root, you write the radicands, that is the stuff inside the radical from both of the radicals that you're multiplying together. You write them inside multiplied together. I said the word multiplied so many times right now, I feel like I'm not sure what I'm talking about. All right, now let's look at this square root for a second. And we have to try to remember how we simplify square roots. In the previous section, when we were simplifying square roots, we said that square roots ask for one thing and one thing only. They ask for which factors are showing up 2 times. If I look inside this square root, I see that 2 is being multiplied to itself 2 times. So the factor 2 is appearing twice inside this square root. And so I'm going to write the single factor 2 outside. And since I don't have anything in the radical left over, I'm not going to write any more radicals. I'm going to leave it just like that and simplify 9 times 2 as 18. And once again, you're welcome to use the Pythagorean theorem to kind of solve this down and do it the long way, but this much faster than having to deal with the Pythagorean theorem. We've got some more examples for you to try in your notes. I've given you the answers here in pink so that you have them, and once you've practiced them, you can check your answers. If you're not sure how to do that and you want to take a look, those of you who are in class with me can find my teacher sample notebook. I have it all worked out here for you to look at. If you are watching this on YouTube and you're not in class, feel free to leave a comment down below. Follow my Instagram. I'll post a picture of these in a little bit later. All right, we've got example 2, which just wants us to find X. This time we're going to find the leg lengths as opposed to the hypotenuse. So this example gonna look a little different, but it sets up the same way. Gonna start off by identifying my triangle. I see that I have a right angle, so this thing is a right triangle. Looking at the legs, I notice that the legs are equal measures. They're both X. I don't know what the measures are, but whatever those measures are, they're equal. This is a 45, 45, 90 right triangle. And I can use my setup from the beginning that said that the measure of the hypotenuse is equal to the measure of one of the legs, doesn't matter which one, just one of them, times the square root of 2. All right, let me get some color going. I'm going to highlight my legs, the legs of the right triangle. My goodness. And then the hypotenuse, there we go. And now once my screen comes back online, don't know why it freaked out. There we go. I'm going to start matching up my colors. So in the red, I see a 12. So I'm going to fill in my red zone with 12. I'm going to grab one of my blue legs, which is X. And now I have to solve this thing for X, which looks like a mess because, my God, I have to deal with a radical. But let's pause for a moment and let's think about what we have written. We have X times the square root of 2. Well, when we're solving for X, we want to get X by itself, which means we have to undo times square root 2. Well, what's the opposite of times? Divide. So I'm going to divide by the square root of 2 because that's what I'm trying to get rid of. And I know that this looks really bizarre to write this square root 2 underneath at the bottom denominator of a fraction. I get it, but this is something I'm allowed to do. I can divide by any number I want except 0. I know square root of 2 is not 0, so this is an allowed operation for me. All right, I'm going to put a little squiggly line here just to show you the difference between my steps. The square root 2 divided by square root 2 will cancel, and that's going to leave me on the left with 12 divided by square root 2, and on the right-hand side, just the X. So far, this is where we stop, because as soon as we get X by itself, we're done. The problem is that with radicals, we have some special rules involved. Like with fractions, if we can write it in lowest terms, simplify, we must. With radicals, we cannot have a radical in the denominator. And so we must do something to this fraction to get rid of the radical in the denominator. To do that, we're going to use a process called rationalization. We are going to rationalize this fraction to remove the radical in the denominator. To do that, I'm going to multiply this fraction by 1. But 1 written in such a way that allows me to deal with this radical in the denominator. I want to multiply it by some other radical such that the radical that comes out at the end when I multiply no longer has a radical. All right, I'm going to pause for a second because I said like radical like too many times. I want to multiply the square root 2 by whatever it takes to turn it into the square root of 2 times 2. Because as we saw in this example right here, when I have the square root of 2 times 2, I can exchange all of it for just a 2. So what do I need to multiply to the square root 2 to turn it into the square root of 2 times 2? Well, I need to multiply it by a 2 because when I have square root 2 times square root 2, that becomes the square root of 2 times 2. What I multiply to the bottom of the fraction, I have to multiply to the top of the fraction because I want to multiply by a value that is 1. If I don't multiply by 1, if I don't multiply by the same top and bottom of the fraction, then I'm going to change the value of this original fraction. This is the weirdest, trickiest part of this. Now, the good news is once you do this a couple times, you're going to start to see a pattern show up in this whole rationalization process. I'm not going to tell you the pattern right now. I'm going to challenge you to see if you can find the pattern. All right, I'm just multiplying numerators together and I'm multiplying denominators together. Notice how I've written that square root 2 times square root 2 as square root of 2 times 2. I'm going to simplify that square root there at the bottom to turn it into just a 2. And now I can simplify this fraction, 12 divided by 2. Now this 2 in the denominator is not going to mess with the square root with the 2 inside the square root. Those can't touch, but I can definitely divide the 12 by this 2 outside. When I divide 12 by 2, I get 6. Since I can't do anything with the square root of 2, that's going to stay by itself. My final answer is 6 square roots of 2. Take a moment, pause the video if you need to, and look for the pattern. Shh, I'm not going to tell you right now. Look for the pattern. Pause and look. All right, now that you think you found the pattern, go ahead and leave a comment down below. Tell me what you think that pattern is. And if you're in class with me after you've watched this video and you want to share with me what you think that pattern is, please do so. I'd love to see what you said. All right, let's look at the second type of special right triangle. That is the 30, 60, 90 right triangle. This is a right triangle whose angles measures are 30 degrees, 60 degrees, and 90 degrees. And these relationship between the sides are a little different. All of them are going to revolve around the shortest side of this right triangle. Please note that the shortest side of a 30, 60, 90 right triangle will always be directly across from wherever the 30-degree angle is. So look for that 30-degree angle, the side directly opposite it that is not creating the 30-degree angle. That side is your shortest side. We're going to abbreviate it with S. The hypotenuse remains in the same spot, always directly across from the right angle. And then the other side is what we're going to call the medium side, the like middle longest side. Okay, so I'm going to color code them this way. Here's the pattern. This 30, 60, 90 right triangle is sometimes referred to as a 1, 2, 3 right triangle, because this shortest side there's 1 of, the hypotenuse is 2 times the shortest side, and the middle side is the shortest side times square root 3. We had to throw the square root in there somewhere. Once again, you're welcome to use the Pythagorean theorem to confirm this and to show that this value will indeed appear. All right, let's go ahead and use this to solve. I'm going to look at this tiny little triangle right here. Sorry, I forgot what I was saying there. All right, I'm going to start filling in some information first. I see the right angle and I see a 60-degree angle, but I don't know what this other angle is. I can use that triangle angle sum to help me fill it out. Triangles add up, all of their angles add up to 180 degrees. So 180 minus 90 is 90. 90 minus 60 is 30. So this angle measure down here is 30 degrees, which means that this side right here, directly opposite that 30-degree angle, that's my shortest side. I'm going to go ahead and continue color coding and identify my hypotenuse. And now that I have my short side and my hypotenuse identified, I can identify my medium side. Hard part's over. Time to use my shortcut. All right, my shortcut tells me that this side 1, this side is 2 times the short side, so 2 times x. And the medium side is the short side times the square root of 3. Now notice when I've set it up this way, I have created a situation where I have a bunch of equations that I can solve. I can't solve the equation with the hypotenuse yet because I don't know what the value of x is. But the long side, the one I've colored blue, I can solve for x. I'm going to solve for x by dividing both sides by the square root of 3. This is going to feel exactly like what I did with the equation in the previous example when I divided by square root 2. All right, I'm going to take the exact same approach, dividing by square root 3, and I'm going to rationalize this fraction because I do not want a radical in the denominator. I'm going to multiply by whatever I need to make square root of 3 become the square root of 3 times 3. I need to multiply by the square root of 3. Whatever I multiply the bottom by, I have to multiply the top by, and now I have this mess. All right, I'm going to continue to simplify here. Just going to multiply straight across. If you paused after the previous example and you already saw the shortcut, that shortcut does apply here, and you are more than welcome to use it. I'm going to continue writing out all the different steps here so that you can see what happens in case you haven't been able to see the shortcut yet. And again, if you think you figured out that shortcut, leave a comment in the comment section below. Happy to take a look at that for you, and I'll give you a heart on that comment if you got the shortcut. All right, I'm doing 15 divided by 3, which is 5. And so now I know the value of x is 5 times the square root of 3. Now that I have a value for x, let me grab a different color. Now that I have a value for x, I can shove that right in there. And I can now figure out the value of y. Okay, I'm going to write it over here because I'm way out of space over there. Okay, y equals 2x. X equals 5 square roots of 3. So y now equals 2 times 5 square roots of 3. To simplify this, I'm going to multiply those coefficients, these big numbers out here outside of the radical. So the 2 is going to multiply to the 5. The 2 will not multiply to the 3 because the 3 is trapped inside the radical. He's stuck inside the square root. So we cannot multiply the 2 to the 3. The same way when we were doing this division over here, we could not divide right here. We could not divide this 3 inside the square root by this 3 outside the square root. All right, I've got a value for y. I have a value for x, which I'm just going to write a little cleaner over here. And I have done everything that this problem has asked me to do, which was to find the values of x and of y. Again, we've got 3 more just like that for you to practice. And once again, if you are in my physical classroom, you'll be able to find my teacher sample notebook where I'll have those 3 all worked out beautifully for you. Again, you're welcome to take a look at Instagram. I'm going to try to post those there for you. So keep an eye out. All right, let's do our last example, the real world example number 4, using our properties of special right triangles. We've got an invention on our hands. This word problem says a company makes crayons that do not roll off tables. It does that by shaping them not like cylinders like our normal pencils, but they shape them like triangular prisms. So that way, if I cut them, they look like triangles. They're going to put them in a crayon box shaped also like a triangular prism. And 16 of these crayons will fit perfectly into its box. This box is 1.5 inches wide. The crayons stand on end inside the box. So the crayons are going to stand on this, and they want to know what are the dimensions of the crayon. All right, there's a little bit more information to grab from this, and that is that the box is equilateral. We have to go back and remember, what does equilateral mean? Equilateral means equal sides. So all of these sides here are going to be 1.5 inches long. So I'm going to transform those into decimals just to make them a little easier to think about. So all of these sides are 1.5 inches long. So we want to try to figure out, the question we've been asked is, what are the dimensions of each individual crayon that fits inside this box. All right, let's take a moment and let's draw the situation that we have so far. All right, I'm going to draw the base of the box, my equilateral triangle. And I know that if I stand up the crayons that are also triangles when you stand them on their base, that 16 of those are going to fit perfectly here. Okay, well, there's one crayon. And I can stick another crayon in this corner. We're pretending these are all equilateral because I'm not the best artist with my mouse. And I've got another equilateral triangle sitting up there. Okay, well, these equilateral triangles, when they stack next to each other, like I can connect right here and I can fit some more crayons in this space. I can do the same thing here. Right here, I think. Yeah, like this. Okay, so now I have some more crayons. And then I'll have another crayon here. And maybe another one here. And then I can put some crayons right here. Okay, perfect. I've got some crayons, 4 of them that sit here. Okay, I can do the same thing over here and stick some more crayons like this. The best drawing ever. Okay, let's see if I've got the right number of crayons. I know there's supposed to be 16 of them in this box. So let's see if I've drawn 16 very badly drawn crayons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I went too many. Okay, so back to the drawing board. This is basically the technique that you're going to use in order to figure out how big the crayons are. Once you know how many crayons are going to fit there, you'll find out how many pieces one of these side legs get cuts into. Once you know how many pieces these side legs get cut into, because that's how many crayons get stacked up in there, just take the length of one of these sides and divide it by however many crayons you think fit along one edge. That's a number sign, not a hashtag. This will give you the dimensions of one side of the crayon. Leave your guesses and thoughts about how many are going to be along one side down in the comments below. And those of you who are in my class will find my drawing worked out in my teacher sample notebook. That's all there is to special right triangles. The hardest part is dealing with this rationalization that's happening here. Please take some time working on this because it's going to be super important in the upcoming sections. Thanks so much for joining me today. Leave a like, subscribe. Again, throw your comments on what you think that pattern is right here when we're rationalizing denominators. Leave that in the comments below. Leave how many crayons you think are going to lie on one edge of this box down in the comment below. And I'll see you guys next time. Bye.